Now come to this ALU part, which is arithmetic logical unit. In ALU we can see we have 18 input and 9 outputs. Among these 18 inputs, these two input EO and SU are coming from directly from the controller sequence. When EO is enabled, the ALU will pass the output. When SU is enabled, SU means subtraction, the ALU will done the subtraction part. And this A7 to A0, these 8 inputs are coming directly from the accumulator, and this B7 to B0 are coming from our B register. And what are these output? And there are we are adding or subtracting 8 bits, so there are 8 outputs, A7 to A0, and this is directly going to the 8-bit bus. And there is another thing named sign, and it has been connected with a I guess it's 7-segment common anode. We have downloaded, we have seen the child sheet from the Google. You can show it, see it from there, and why we have used that. As we have improved our project, when the subtraction command is on, suppose we are subtracting 5 from 4, so we'll get a minus sign, -1. So this sign will send a signal to this display, and here will be a minus sign. Also, if we subtract the same number, like we minus 4 from 4, there will also be a minus. Minus 0 or plus 0 means nothing. It's always the same. So let's take a tour on our ALU. So this is our complete ALU. From the zoom out portion, it's look like a complex circuit, but let me ensure you that it's easy. We have connected so many logic state and logic probe to go and make a very good understanding of this circuit. If we zoom in, we can see that there are it's nothing but this portion is nothing but a 1-bit full adder. So we have connected 16 1-bit full adder. If you look closely, so why 16 1-bit full adder? We can also make the ALU using 8 1-bit full adder. That will do the same addition or subtraction part. We have used 16-bit as we have already told you that we want to show the sign plus or minus. So this portion is working. This left hand side where we have 8 1-bit full adder, it's actually doing the summation or subtraction part, and the right hand side part, it's doing the 2's complement portion. So we already if you have a knowledge of adder, you will know that if we connect a XOR gate with the adder, it will add as a subtractor. We have EO connected here, connection here. EO has been connected with the final output, and it has been buffered with all of the sum output. And we have also connected SU input here. SU will be activated when we want to subtract. If SU is 0, this B0 will directly go to this XOR gate, and this will be passed through this. And we have done another thing. If you look closely, that in our very first 1-bit adder, we have grounded the value. And if you can remember, this connection was carry input. As we want our first carry to be 0, that's why we have grounded it. And same here also, in the first adder we have grounded the value as we don't want any carry. So, and we have connected the last carry. We have not it. We have not getted it, and the SU is going here, and this has been ended. This is output of sign, and this sign input is going to the second this XOR gate. And this XOR gate is actually doing, when it's activated, it's actually doing 1's complement. And how we do 2's complement? We make a number binary, then we make it 1's complement, and then add 1 to make it 2's complement. And if you look at this carry has been ended with the SU, and this result has been connected with the very first very first adder, not any other adder, the very first adder, to add 1. So let's give some input here. Suppose we are adding 4 plus 4, it will give us 8. So when we are adding 4 plus 4, it equals 8. This is doing the summation part, and if you look at this, this is 0 and after not being not, it will be 1, but ACU is 0, so this is not, this is actually 0, and this 0 and 0 will give us 0. So as the input of the XOR gate is 0, we are not doing actually 1's complement here. So it's the carry is also 0, so we are not adding 1 also, we are not adding 1 also here. So what's in the left hand side being passed through the right hand side. So in the sum case summation addition case, we are directly passing the values at the output by doing some logical circuit. So now let's do another thing. Subtract 5 from 4. To subtract 5 from 4, we need to enable ACU. So 5 minus 4 is 1, so sign is 0, as we are subtracting a smaller number from a bigger number. So if you see, this is 0. When we are subtracting 4 minus 4, our sum is 0, 0, 0. All the sums are 0, so we need to add 1. So the last carry is 1, it's being or not, so 0. ACU is 1, this is also 0, so the sign is not activated, but this AND gate is activated. So we'll, as our this result is 1, we'll add 1, add 1 with the value. When we are subtracting, every case of subtracting a smaller number from a bigger number, we are adding 1 with the sum. So here this 1 is coming, this 1 has been being added, the carry is going here, and the output has been taken from here. So we are getting 1 here from 0. We know if we add 1 with 8-bit 0, it will show 0 0 0 0 0 0 0 7 1. Sorry. Now take now subtract 4 from 5. So we are subtracting a bigger number from a smaller number, we'll get 1, and our minus sign will also be 1 activated. So take a look here. When you are subtracting 4 minus 5, the sum here is also 0. If you take a look, all sums are 0, but this carry is also 0. So this 0 will pass through here, and this will 1. ACU is 1, so the sign will be activated. Sign will be 1, and this 0 and ACU, this is 0 1 will be 1 0. So as sign is activated, this XOR gate will toggle as the two inputs are same, the XOR gate will toggle the value. It will act as a NOT gate. Very easily, if I say that the XOR gate will make the sum its 1's complement. This 0, this is 1, this is 0. So this 1 will come, this 0 will be toggled here, like 0, 2's complement, 1's complement of 0 is 1 here, the 1 will come here, 1 will be 0 here. So this, but like this, it's inputting all the element here. So, and as our here we are getting 0, we'll add 0 here, nothing. So this 1's complement, and we are adding 1 here. It we know if you want to make 2's complement of a number, first of all you make it 1's complement, then add 1, it will become 2's complement of the number. So the here input is coming, and the input is 4 minus 5, it's 1, and the sign is also 1. Also our circuit acts like that. If we if we delete, if we subtract the same number, it will also show us a minus sign, and the output of 8-bit will be 0. If we subtract this, and this will be 0, and the sign is also 1. So here was our total ALU, arithmetic logical unit. If you want to learn a very deep knowledge about this, you can Google it, how to make 2's complement circuit. So let's finish it here.